Hello, this is Bruce Wollenberg again. This is lecture 11A, the first lecture in our set on power system security. That word does not mean security in the sense of the power system resisting intrusion or attack. It's not like what you would say the security of a building is. But what we're implying here is that how secure is the power system against complete collapse? We want to prevent the power system from blacking out, given that there's a set of natural outages caused, for example, by lightning or caused by just a failure of a component. I've got these two magazine covers, one from Time, one from Newsweek. The one on the left is taken from an issue of Time magazine in August 2003, and so is the one on the right. And what they are showing are buildings in New York City. The one on the right hand side, of course, is the Empire State Building, and oftentimes these outages hit in New York City and cause blackouts. Now you'll notice that there's a few lights in some of the buildings that are on. Probably they have backup generators, but outages or basically not paying attention to security of the system can cause blackouts, and oftentimes the blackouts, if they happen in rural areas, you may never hear of it, but when they happen and they black out a large metropolitan area like New York City, or on the West Coast, San Francisco or Los Angeles, etc., in the U.S., we get lots of publicity for it, and lots of people calling for measures to be taken. It's a wonderful time for politicians to pontificate on that subject that they know very little about. Okay, what are the kinds of outages that can occur? We might need to take a transmission line out for servicing. We might need to take a transformer or a circuit breaker or a disconnect and so forth. We might need to take them out on a certain schedule for people to get in there and isolate it, ground it, and then work on it. It's you have to be very careful of scheduling the outages, and you have to study the system and say, if I take this out during the daytime, am I going to be able to get through the peak load during the afternoon? If not, then we got to pay the construction people double time and let them do it at night on the night shift, and whenever the load is low. So you have to be very careful when you take outages out for scheduled work. Forced outages are those where we have no control over it. It just happens. It's not done by an operator or by a schedule. It's due to a random event such as a lightning strike, an insulator suddenly fails and arcs and explodes, a transformer suddenly develops a fire and has to be taken out, etc. It can go all the way from small components like an insulator all the way up to big transformers, and to the power plants themselves, to the generators, can suddenly develop an internal fault, or they can have some other problem and have to go offline. Okay, they both, forced and scheduled outages, cause trouble for the power system. Now, the organization in the United States that has been around since one of the first blackouts. It was formed just after the 1965, one of the first big blackouts in the U.S. And it now stands for the North American Electric Reliability Corporation, and it works in conjunction with the federal government in the U.S. to set standards for operation, set standards for maintenance, for calibration, etc., etc. They have classically had a rule called the N-1 rule, and it simply means if I have n components to start with, then n minus 1 means I have one outage. And it says that no generator outage, no single, I should say no single generator outage will result in so large a frequency drop that other generators will be forced offline. We'll learn more about this generation and frequency in the next set of lectures on generation control. But suffice it to say, when you lose a generator and you're short of generation, frequency starts to drop until all the generators can be brought up a little bit through governor action to restore the frequency. But we don't want that frequency drop to be too large. So we have to worry about the generation outages. No single transmission or generation outage will result in another component's experiencing such a large flow or voltage change that new limit violations occur. Now what we're saying here is that if a generator goes out, or let's say a transmission line or transformer goes out, all the flows are going to change on the system, and many of the transmission lines will experience an increase in flow. That can cause problems. If that increase in flow is so big that the breakers are triggered by relay sets to open the line, then the first outage caused another outage, and this can get into what's now called a cascading outage, where one outage causes another, and then that causes another, and things just get bad, and the system goes bep, 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 like the proverbial set of dominoes knocking each other down, and the power system goes black. Another phenomenon that can occur, we'll talk about quite a bit here, is that whenever you have an outage, you have increased reactive problems on the system, and the voltage will drop. And if the voltage gets too close to a collapse point, the whole system can collapse due to what we call a voltage collapse on the power system. Okay, to try to make sure that your system is secure, we have three major functions. First is system monitoring. The idea here is that we'd like to know, are there any components with parameters out of limit? And what we're going to do is we're going to sample data from measurements. We're going to run all those measurements past limit checking in our SCADA system, and we're going to run state estimation to get very accurate values of all of those quantities and test those flows and voltage magnitudes against limits that are limit values that are stored in the computer. Anything that comes out that where it says it's either too much flow, too much current, or too low a voltage, we put an alarm, and the alarm is a literally, well, there's an example of alarm, okay? My cell phone giving me a small alarm. And the value of the alarm is that it rings a bell, like you heard there, and that alarm gets the operator's attention, and the operator has to do something. First thing they do is they go and they acknowledge the alarm. They touch a button on they touch a place on click. I should use the right terminology. They click on a screen, and that says, I've seen the alarm and I recognize it, but then they're trained to go do something. They have to then take some action to fix the problem on the system. So if the system is not experiencing any alarms, meaning there's nothing overloaded, no voltage is too low, well, the next thing is we want to know, well, what if I have an outage, and that causes an alarm, or that's going to give me an alarm. So the what-if analysis says, are there any of those components that would be out of limit due to the outage of another component? So this is the what-if. What if a generator goes out? What if a transmission line goes out? What if? And we have to test all the components for possible outages. Okay, called contingency analysis. That's the more formal, but I like the what-if analysis. Last of all, if you do get to the point where a what-if tells you that you got a problem. If you lose line A, line B is going to overload, then you want to do something about it. And one of the things that you can do is to run security constrained optimal power flow, which we explained in the previous chapter, which will produce a dispatch that will protect you against those contingencies. Okay, so here's just some simple use of security analysis. We first do an optimal dispatch. Okay, now this doesn't have any security limits in it, so we say, okay, here I've got two units. I've got a 700 megawatt, and this is a little smaller, 500, and we're supplying 1200 megawatts. Now, if I'm supplying 500 over two transmission lines, they each load up to 250 megawatts. Now, we have to tell you that these lines have a max of 400. That's the max. So, we have the following problem. Post-contingency, I lose one of these lines. The breaker's open because, who knows, I had a lightning strike here in the middle of the line, and therefore I had a fault to ground, or maybe I had an insulator that failed and started to short out. So I had to open the transmission line. As soon as I opened it, this 500 is now coming in here, and this line here is going to heat up, literally heat up, and start to sag and to fail. So the post-contingency condition of that first outage says we've got an overload. Now, the secure dispatch, if the operator, this gets detected by a what-if test, says your post-contingency state has an overload, then we run a secure dispatch, and what it would do is it would say, well, I can load this up to a maximum of 400, and then I have to pick up the other 100 here. So I had to run this one down, and I had to run this one up. This one from 500 to 400, and this one 700 to 800. I'm still supplying the load, but now if I get an outage like this, then I'm at 400 here, and I'm at 400 here. I don't have any overload. I'm secure. So I have a secure post dispatch. So there's your conditions, again, going from the post contingency that would be detected by the contingency or the what if analysis. Then I do a secure dispatch, and I can test it again, and the secure dispatch says that in fact things are safe now. It may be, it very, very likely may be, that this is more expensive than the one where I had 500 over here, and so the cost is greater. For example, if I was doing the 500, this may be a very inexpensive source of generation, like a hydro plant or something, and I really want to buy as much as I can. They're willing to sell me 500, buy it all. It's cheaper than I can generate it. Unfortunately, the system is not secure. I've got to back off, and I got to run this down and only buy 400 here and then 800 here. It's going to cost me more, but it is secure. Okay, now if we have generator outages, the power imbalance between the load and generation results in a drop in frequency. So when we get this drop in frequency here, then we have to make it up, and what happens is every generator goes up according to the frequency control of the system, which are governors on each generator. However, if there's not sufficient what we call spinning reserve available, meaning a generator can't go up beyond its upper limit. Well, if most of your generators are right up against their upper limit or very close to it, and then you lose one of them, the remaining generators can't go up. They're going to hit their upper limit, and they can't make up for the total generation that you've lost. And now your frequency is just going to start going down, and the system will black out. The generators will go off one by one, and the system will black out. So we have to make sure, we have to do a spinning reserve test and monitor that. So that's one of the what ifs. What if I lose a large generator? And it's simply a matter of doing an accounting of how much the largest generator that could be lost. Sometimes it's the two largest generators I have to carry in a spinning reserve. Line flows can change as generation is shifted to other generators, so that's another check that you can make on as a what if test. Transmission outages. A line outage means flows shift to remaining lines. The remaining lines can overload. The reactive losses can increase on the remaining transmission lines, and bus voltages may drop below acceptable limits. Here's, just to tell you, here's some of the effects of a transmission loss. A transmission loss here. It says that for all lines, the line consumes reactive power as I squared X for the transmission line. So that's a loss. That's a reactive loss. You also don't have the reactive gain that you normally would, because if the voltages go down, so V squared times the B cap at each end summed over the lines, that's a source of reactive. That's a negative loss, if you will. So this is a loss, this is a negative loss, and then reactive power injected into the system from fixed capacitors is also a negative loss. So if you add all of these up, it turns out that if you want to increase losses, increase the current flow. Well, a line outage will increase current flows on a large number of lines around the system, and the voltages will decrease. Well, if these decrease, then this is less negative, meaning that you're losing. So you're increasing this loss, and you're decreasing this, which is really a source. These are really supply. So the reactive power on the system gets more and more unbalanced. You get more and more losses in the transmission lines, and you're not getting as much coming in from the capacitance on the transmission lines or the fixed capacitors. And so very often what will happen is that you will get the increased reactive demand from the losses on the system, and the system will result in very high demand on the generator. So I've got increased reactive losses, decrease in the charging and the capacitor supplied reactive power. So I have a great increase in the VAR demand on the generators. Well, generators can't go that high in supplying reactive power, and when they hit their limit, then the generator voltages start to drop. When the generator voltages start to drop, that makes everything worse. Okay, and we'll go through an example here. This is our 6-bus system, and this is case 4 from Appendix A of Chapter 7 on security. Bus voltages 4, 5, and 6. If you look down here in the table, I've highlighted them in green. These bus voltages are low to begin with. They're 0.99 and 102. The maximum voltage is 107. The min is supposed to be 105. So I'm already below some of the where I want these voltages. Reactive power and losses go positive and large. Now this is when I doubled the load on bus 4. The reactive power, notice the total losses, Q losses, is a negative loss, is a loss there, 33. In addition, bus 4 now I've raised the load to 200 megawatts, 30 megavars. Several transmission lines here are experiencing overloads. And the max flow here is 100 megawatts, it's 138. Its max on this one is 60, it's 68, and so forth. So I've shown that a large increase in load on one bus, and I've got problems with voltages down here, these voltages, and I got problems with these line flows as well. Now, operations needs to know which outages will cause problems. The solution we call security analysis, call it contingency analysis, or what if. Need to study what if this component is lost for each component on the system. We'd like to run an AC power flow for each transmission line or transformer outage and simulate generator outage and governor response for all remaining generators and run an AC power flow. The point here is that this is a very large computational task. It may, from my experience working on large control centers, this is one of the largest computational tasks taken up by the computers that run the power system. The other one, by the way, is the alarm processing, making sure that everything gets compared to a limit and then brought out to the operator. So those two functions, and they're both kind of in parallel for keeping the system secure. Here is the overall flow chart of it. System conditions we get from the state estimator. Simulate an outage of generator I using the system model. Any line flows, give me an alarm message. Any bus voltages, give me an alarm message. Then go back and do all the other generators. Then do all the lines. We simulate an outage of line L, etc. Any alarm messages for overloads and voltage limits, and we do all the lines. So we loop through all the generators. We loop through all of the transmission lines. It's an exhaustive procedure, especially when we're doing it with AC. Now, many people say, well, you can use the linear power flow. If I use the linear power flow, I lose all information about the bus voltages, so that we can't operate the system that way. So AC power flow is ultimately the choice that you're going to make if there's any concern about voltage magnitudes, reactive effects. Thank you very much.